We're now moving out of the world of calculus and into the world of vectors. We're going to start with geometric vectors. Anyone who's already taken physics knows that vectors connect numbers to the real physical world. But vectors are not just numbers. They're quantities with both direction and magnitude. They are the mathematics behind every force that pushes, every velocity that drives any motion, every wind that blows, and every current that flows. Whether we're launching spacecraft, designing a bridge, or creating 3D animations, vectors are the language we use to describe and control movement in space. Don't worry if you haven't already taken physics. This unit will give you everything that you need in order to be able to do actually the next 3 units, a basic understanding of what vectors are. Before we start working with vectors, there's some terminology you need to be familiar with. We encounter different quantities in our everyday lives all the time. It takes me 25 minutes to get to school. I walked 5 kilometers yesterday. The car was caught going 160 kilometers an hour eastbound on the 401. Some of these quantities are scalar and some are vectors. A scalar quantity is simply quantities that have magnitude only. Things like length, mass, time. It takes me 25 minutes. I walked 5 kilometers. Vector quantities have both magnitude and direction. Things like force, 10 newtons up, velocity, 10 kilometers per hour east, acceleration, 9.8 meters per second down. We'll know that something is a vector because vectors have special notation. So we can see here, if we look right here, and I'm going to draw it bigger over here, you'll hear me say that all vector quantities wear hats. They have an arrow above them. So if you have letters, 1 or 2 letters, that are denoting some type of vector quantity, they will always have that arrow on the top. They can also be represented, though, simply by an actual arrow. The length of the arrow can be used to denote the magnitude. So the longer the line, the greater the magnitude. So we have 2 vectors here, vector v and vector ab. Should have a full arrow over the top of it. Vector AB. The longer the line, the larger the magnitude. So if I have a vector that's this long versus a vector that's this long, vector A will have a smaller magnitude than vector B. So when we're using arrows, the tip is the part with the arrowhead. So this is the tip. The part that doesn't have that, or the starting point, is the tail. And you'll hear me talk about when we start adding vectors, tip to tail and things like that. So the tip is the part with the arrowhead and the tail is the starting point. And the direction that the arrow points is the direction of the vector. Now, this is a hard or tricky thing to wrap our heads around because we do have both magnitude and direction, but right now I'm going to tell you that a vector has no fixed position. So a vector, what really matters with a vector is how far it goes, its magnitude, and which direction it points, not where it starts from. You can move a vector anywhere along a plane or in space as long as its length and direction stay the same. It's the same vector. I can draw an arrow anywhere on this page. I can draw an arrow down here, and I can draw an arrow up here, and so long as they're pointing in the same direction and they have the same length of the line, it's the same vector. It doesn't matter where I draw it on the page. This is different from a single point stuck at one location. A vector's free to move because it describes motion or force and not a fixed spot or fixed place, a fixed location. Another idea that we need to be familiar with is that equal vectors have the same magnitude and direction. So if we take a look at this parallelogram, if each line in the parallelogram is a vector, then we can see that vector AB over here is going to be equal to vector DC over here. They have both the same magnitude and the same direction. They're equal in length and they're going in the same direction. We can also see then that if we reversed this, we could say that vector BA is equal to vector CD. They are also going in the same direction. So, so equal vectors have equal magnitude and direction. Just like vectors going in the same direction can be equal, opposite vectors, if they have the same magnitude, will have opposite directions. If we go back to our parallelogram, we could say that vector AB over here going in this direction, it will be the opposite of vector CD, because now CD, if we look, is going this way. That means it will have the negative. It will be the negative of CD, or we could say that AB is opposite of CD. That's really what that negative denotes. We can see this in the second example. So if two vectors are opposite, such as AB and CD down here now, we have A, B, C to D. One is the negative of the other, so they go in opposite directions. AB is going up and to the right on the page. CD is going down and to the left. They have the same length of line, but they are pointing in opposite directions. We also can talk about vectors being parallel to each other. So if we take a look at this trapezoid, we can see that the lines PQ, and if we considered those as vectors, PQ would be parallel to RS, to vector RS. So PQ up here will be parallel. They don't have the same magnitude, but they are parallel to each other. We also could say, it would be equally correct to say, that PQ is also parallel to SR. In this case, we're not talking about direction really with that one at all, just that they are parallel to each other. Some other examples of vector quantities that you may or may not be familiar with. Again, this idea of force. So the force of gravity has a well-defined magnitude and acts in a very specific direction down. The force of gravity is measured when you step on a scale. It's not actually your weight, and I'm putting that in air quotes. You can't see me, but I'm putting it in air quotes. Force is a vector quantity, and it's measuring the force of gravity acting down on you as you step on that scale. We just happen to translate it as our weight. Displacement is also a vector. So displacement is just when you move from one place to another. So if you walk from point A to point B and travel in a certain distance in a certain direction, that's your displacement. Displacement is a vector quantity, and displacement is different than just your total distance traveled. So if I were to start at my house and I was chasing my dog, who goes on this really wild path to end up right here. Here is my dog, and he's quite happy about the fact that he's run away, and I am chasing him. If I were to measure the distance from where I started to where he ends up, I would be traveling this great big long circular path, winding around all over the place to get to my dog. That would be the total distance. That is much further than his displacement from me at the end from where we started. So this would be my displacement. That is a vector quantity. I can measure the direction of that. The distance is all of this windy spaghetti up here and is just the total distance that's actually traveled. Another one that we can think of as a vector quantity is a magnetic field. We know that some magnets are stronger than others. Some are strong, some are weak. All will cause a compass needle to swing around and point in a particular direction. That means a magnetic field is a vector quantity. Often our questions with vectors will be more practical or real-world type situations like this question. So, a swimmer swims due east at 3 meters per second. It's a vector. It has a magnitude of 3 meters per second and a direction of due east, meaning that they are heading just straight east. The current runs south at 4 meters per second. Again, a magnitude and a direction. Find their net speed and direction. I want those of you in physics to just make note that math sometimes uses different language than physics. The net speed and direction is really just our resultant velocity, what I would call V with a capital R on its side. And that resultant velocity vector actually implies both magnitude and direction. So if we're finding the net speed and direction, we really are finding that resultant vector. So what do I mean by a resultant vector for those that aren't familiar with that? Well, we're going to draw a diagram and I'm going to show you what I mean. So The very first thing we need to figure out is what directions are we talking about? And the easiest way to do that is to just simply draw a small compass rose with north, south, east, and west on it so that we know we have things pointing in the right direction. So now I have a swimmer who's swimming due east at 3 meters per second. I am going to draw a line going in the easterly direction. This is the velocity of my swimmer, and that velocity of my swimmer is 3 meters per second going east. The current in the river is running south. That means that it's going from north to south. So that means that the current in the river is going from the top to the bottom, or north to south, and that's at 4 meters per second. And that's the velocity of the current. I'm going to label that C, the velocity of the current. So what are we really trying to find out? We're trying to find that resultant vector, or where is the swimmer actually swimming and at what speed are they actually swimming. That's what I'm referring to as the resultant vector. And that's going to tell us the direction and the speed with which the swimmer is going when they're trying to swim east, but they're being pushed by a current going south. So again, we're going to need both magnitude and direction to solve this problem because it is a vector. To find the magnitude, we are simply going to use, well, we're going to use what we know. Some of you may have already said, oh, I know what this is already. So to get the magnitude, we could use the Pythagorean theorem because this is a right angle triangle. But this is also one of those special triangles. This is a 3, 4, 5 special triangle. So without even doing any math, I know the magnitude of my resultant vector is going to be 5 meters per second. That's the magnitude. Now I need the direction. So my direction, this is a right angle triangle, so I can use my primary trig ratios. I just have to figure out which one I need to use. Well, I have this is the angle here that I'm trying to find. That's the direction. So I can use my primary trig ratios, and I have my opposite and my adjacent sides that I was given in the question. Therefore, I'm going to use tan. So tan theta is equal to opposite over adjacent, 4 over 3. So that gives me an angle of 53 degrees. Now we need to put it together, and we need to put some context to this 53 degrees because we have to give it a bit more of a direction. I could say 53 degrees, and that could be 53 degrees from anywhere. So we have to give it a starting point and an end point, and this is what I mean. So we're going to put it all together. My resultant vector is equal to a magnitude of 5 meters per second. This is where I'm going to tell it what direction this 53 degrees is coming from. So this 53 degrees, if we were to come back up here and put our compass rose here, this 53 degrees is starting in the easterly direction and going towards the south. So we are going to say that this direction is east, 53 degrees towards the south. That's how we're going to denote it. And that is the answer for this particular question. Okay, so there is some homework questions for this. It is posted to the VLE, and take a look and see. So work on those practice questions. There will be an exit ticket for this lesson as well. So watch for that. As always, if you have any questions, feel free to send me an email.